We'll be talking about probing the intergalactic medium during the epoch of reionization using 21 centimeter signal observations.
Uh, Hello, am I audible? Okay, good. I myself Raghunath Ghara. I am a Ramanujan Fellow at IISc Kolkata. In this talk, I will be basically following the philosophy which was introduced in the morning by Gerald. So that says like the intergalactic medium and characterization of that and interpreting the H1 21 centimeter observation to derive constants on intergalactic medium properties are more interesting compared to the source model. I will basically talk about current understanding about the states of the intergalactic medium during epoch of reionization, what we can get from the observation of 21 centimeter signal data, what we have. So this type of light cone we have seen many times. What I wanted to highlight is that the nature of signal during the cosmic dawn is very different than what we expect the nature of signal is from epoch of reionization. So the nature of signal during cosmic dawn is mostly dominated by the fluctuation of spin temperature, while the medium is mostly neutral. So you can imagine that the signal is basically combined of emission region and absorption region. Emission region is positive, absorption region is negative signal. While during the epoch of reionization is the large ionized regions which dominates the fluctuation in brightness temperature. Although we don't know where these particular two epochs lies, so there might be a combination of these two scenarios. So for this particular presentation, I will consider all different models, which might be possible scenarios during redshift range of 8 to 10. So in this talk, as I said, that focus will be on the properties of the interactive medium, which can be quantified by few quantities. What is obviously like the average quantities, for example, fraction of ionized regions, fraction of, let's say, emission regions, gas temperature, maybe mean brightness temperature, and somewhat morphology description of these emission or ionized regions. Now, I have put this particular thing in bold because morphology or the characteristics of these ionized or emission regions, to study those, these become quite complex because as you see, after some amount of ionization or heating done, the distribution of emission regions or ionized regions, those become very much complex shape. More or less, like after 10% of ionization, you will find like percolation happens. So overall, like what we will find that there is a big tunnel which connects like all over the simulation cube. It's not ionized or it's not spherical region anymore. After the overlap happens, it will have a very complex shape. The first thing is like how to quantify the morphology of such a complex nature of the distribution of neutral regions or ionized regions. So there are different approaches already existing in nature, in the studies, which tries to quantify the morphology of such emission or ionized regions. For example, here I'm showing for demonstration purposes 3 different models. There are many other approaches as well. So for example, like this mean free path method, which basically shoot rays in random direction from random points inside regions of your choice. That could be from your ionized region, that could be neutral region, or that could be emission regions or absorption regions. And then it records the length of those rays until it basically hit the boundary of that particular type of regions. Here for demonstration, I am showing emission regions and for different fraction of emission region states. And as you see that this is showing the PDF of those ray lengths. And this is what will be the outcome from this mean free path method. If you go for granulometry method, which is based on application of Minkowski subtraction and addition, basically applying spherical filters, you will get a completely different probability PDFs. While in the friends of friends algorithm, which relies on finding neighboring tails of same category, you will again find distribution of very different natures than the previous two. So the point what I wanted to highlight here is that different algorithms, they finally give some results which are very different than others. What we need to do is when we are using one type of such distribution, we have to keep in mind the methods which we have basically used for that. It is not very clear which particular algorithm is best to use for us. Or, for example, like Gerald was highlighting about a framework which, let's say, connects the observable directly from the intergalactic medium parameters, which for till now doesn't exist or doesn't work that well. So for this particular purpose, I am not going to this argument that which is best to use, and I will be only focusing on the simpler framework method to use in simulation, which from now on, I will be using this mean free path method, and you have to keep in mind the used assumptions or method for that one. Right. The good thing about this one is that the observable, which is the power spectrum, it varies when you basically change the morphology of these signals. Here, for example, these two are cosmic dawn scenarios, where this is heated region fraction is 30%, here it is 5%. Here you see that, okay, the size of these emission regions which are in red, this is quite big compared to the other case. And the shape or amplitude of the power spectrum is distinctly different. So that to say that an observation or measurement can actually be used to distinguish what is like the nature of such a distribution or something like that. So of course, like the distributions or the size of these emission regions are generated by the source present in the universe. But for now, I am not talking about this one. I'm just interested in the size of these regions, for example. For now, I'm just keeping the intrinsic source properties and things like that. Another good thing which has been already talked extensively yesterday, that we are now at a time that many interesting results are coming, although those are at upper limit levels. For example, like we have results from HERA, LOFAR, MWA, which has quite good upper limit results, which has ruled out some Riemann scenarios, and which will be very interesting to probe the properties of the intergalactic medium. And I will be basically talking how we can use some of them to constrain the properties of intergalactic medium during this particular redshift range. As I am repeating that for this particular talk, I will be focusing this redshift window from redshift 8 to 10. Now, this particular plot is as a function of redshift and power spectrum for a fixed K or wave number, but a measurement somewhat looks like this. So this is a recent measurement from LOFAR team, which has put this upper limit from 140 hours of observation at 3 different redshifts, redshift 10, 9, and 8. Right? So here, what I will demonstrate is how we can use such a upper limit results to characterize or at least put some constraint on the properties of the intergalactic medium during these particular redshifts. Now, you notice that these are upper limit results, but not not a detection. That means like the brightness temperature power spectrum somewhere lies below these particular numbers. And we have to also keep in mind that in our analysis. Now, obviously, as there is no framework existing which connects directly to the intergalactic medium properties to power spectrum, We have to rely on some modeling of brightness temperature cube, which later we basically estimate the power spectrum and compare with our observation. And here, let's take any of our simulation codes. Here I highlight my code, which is Grizzly. This is a code based on n-body simulation outputs and 1D ready transfer. It takes several source parameter as input, and for a set of source parameter is basically generate brightness temperature in 3D cube, and thereafter we generate our statistical quantity of our interest. In a Bayesian framework, we basically combine this code to explore the parameter range of the source parameter range and put constant based on the upper limits. It's also need to define a likelihood for this upper limit. Now, as the main focus is not on the properties of the source parameter or source, not on the source parameter, but on the IgM quantities, what we do, so our main Bayes analysis are run on source parameters, and later what we do is we derive IgM quantities, which are in this case ionization fraction, heated fraction, mean gas temperature, and some characteristic size of these heated regions and full width half maxima. So a typical distribution of this mean free path bubble size distribution looks somewhat like this log normal type of distribution, which you can now quantify this distribution by these two parameters. One is this R peak, where this PDF has this maximum, and the full width half maximum. So this is overall an overview of the framework which we will be using. Now, for the Bayesian inference, of course, we need to choose a range of the parameters. So the analysis or the constants which we will get, both on the source parameter as well as on the IgM parameters, will be highly dependent on this explored range or the priors which we use. This is one thing we need to keep in mind. The list of the source parameters are this ionization efficiencies, which will control the ionization fraction, minimum mass of UV emitting halos, which will control how many sources are contributing to ionization. M mean X is a minimum mass of X-ray emitting halos, which will control like how many sources has contributing to heating or how patchy the heating will be. And Fx is a parameter, which is X-ray efficiency, which will basically, it will decide whether the heating will be very efficient or not. Now, derived IgM parameter list is these: volume average ionization fraction, gas temperature, average gas temperature, mass average brightness temperature, volume fraction of region which are hotter than the CMB temperature, and two parameters which basically quantifies the size distribution which we derive from mid-free path method. Right. So in this plot, what I am plotting is 1,000 randomly chosen Grizzly model power spectrum, right, from our 10 to the 5 Grizzly power spectra set. And on top of we are plotting, so this for SIB9, and we are plotting these points are lower new upper limits. As you see that some models are actually above these points. So these are the models which we can say that these are not the possible scenarios. So these are the rule out models. Right. So this dashed curve, which I am presenting here, this is for the scenario where IgM remain neutral and no X-ray heating. So LOFAR is not able to rule out that particular scenario yet, but yeah, over more integration time, it will rule out this scenario, and after that we can say that, okay, we expect the at SIB9, the IgM to be heated. But for now, like what we find, like overall, like 10% of these models have high probability to be ruled out, so which are highlighted in the color. Otherwise, other models are presented in gray. Scenarios are also similar when we consider other two redshifts, redshift 8 and redshift 10. So none of these upper limits are able to rule out this neutral and cold interactive medium model. And if we do a statistics on these color models, which has quite high probability to be ruled out, then what we find is that most of these models has neutral fraction quite low. That means like these models are mostly dominated by spin temperature fluctuations. And also like this here, what we find is like temperature is also quite low, and it has a quite significant size of characteristic size of emission regions or ionization regions. And also value-wise, this broadening of this mean free path PDF, this is also quite large. This count number doesn't make sense here because like it will depend how many actually models are in our state. But overall, like this nature of or the histogram, this give us some information. Now, here on, if I talk about the Bayesian inference, for that we need to define a likelihood for a given set of parameter, theta. Two types of exploration can be done. One, assume that, okay, we will only consider power spectra at a certain redshift. And we don't, so there are uncertainties how these parameters, source parameters are changing with redshift. So we don't want to go into that complicacy and only do the analysis on a single redshift basis. In that case, for a upper limit with a Gaussian error bar, the likelihood of exclusion likelihood looks something like this. In a scenario where we assume our set of parameter, which are source parameter, doesn't have a redshift dependent, if we want to combine all different redshifts, then the likelihood, exclusion likelihood will look like something like this. So if we do the analysis based on the previously shown prior, then from lower recent upper limits, the distribution of the source parameters from MCMC looks something like this. So here, what one can look is that the excluded or the disfavored model have two preferred nature. One is M mean has to be quite high, as well as zeta has to be quite high. That means like the disfavored model has large UV emissivity and also small number density of sources, which will eventually create a very patchy reionization. Same is also true for fx and mnx parameters, which will basically create a very patchy fitting history. So these are the scenarios which are basically giving us these extreme models, which basically are disfavored by lower upper limits. Now, if we do the same, if we use the same chains, which are initially derived from the source parameters, and produce the procedure distribution on the IgM quantities, these look something like this. As I said, like most of the disfavored model has quite small value of ionization fraction. Also, same it is true for heated fraction, and it has a quite large value for this characteristic size of emission region or ionized regions, and also the broadening of the PDF is quite large. So I'm summarizing the results in this table, but the red, these values are for the single Z scenario. And this is at redshift 9. I'm only considering this red has been derived considering only redshift 9 power spectra values. So these are the numbers has been used. And you see that these numbers are quite similar. So these derivation doesn't depend on each other, but to sigma level, these numbers are quite similar. That to say, the extreme models which are highly probable to be ruled out, that has quite similar intergalactic medium properties. So a certain stage like The nature of intergalactic medium will be similar, which will give us these models. Of course, when we combine different three redshift results in a joint analysis, what we will find that there is a redshift evolution of the constants, which is expected. One problem what is there in this joint analysis, which we need to realize, is that always this analysis will be biased by the strongest upper limit. In this case, the strongest upper limit is at redshift 9. So there is, like, you will find that these numbers are quite similar, although, I mean, as there is already a evolution and this joint analysis is done on this source parameter, the IgM parameter, I mean, naturally it will have shown this evolution. Interpretation-wise, what we have found is that two types of basically models has been ruled out. One model is basically driven by fluctuation in ionization fractions. This is one of such snapshots of these models, where these regions in yellow are ionized regions, and regions in green are actually cold region. These are neutral region, but unheated regions. Second set of models are this spin temperature fluctuation model, where regions in yellow are actually neutral region, but heated region. These are emission regions. And in green, these are absorption region in negative signal. Now, of course, LOFAR is not the only instrument which are probing at this redshift. There are other instruments which has produced very useful results. And if we combine all of these upper limits from MWA, HERA, and PAPER, so the picture looks something like this. Now, as you see that at redshift 8, for example, HERA limit, these are the strongest limits. And it is ruling out this scenario where the IgM is unheated and neutral at redshift 8. So it is consistent. So the HERA paper has an interpretation paper already, and they had already highlighted this one. So if we combine all these things in a joint analysis, so that will be basically mainly driven by HERA results at this redshift. And the joint analysis and single redshift analysis, including all available information which we have at these three redshift bins, can be shown by this particular PDF distribution, where you see that now at redshift, for example, 8.3, this limit on the disfavored model has been covering a very quite large amount of the parameter space. So this is probably a time that we can now switch our problem. Here, what we are focusing is on the disfavored model, but probably one can include HERA in their analysis and do statistics on the valid model. This will happen eventually with other telescopes as well, when eventually, like, the upper limits will go down and many of our models will be ruled out, then we will be basically focusing on our valid model statistics. For now, what I wanted to mention is that this intergalactic medium properties is very important to study, as this breaks the genesis of the dependence of source model in different codes. So what we expect is that the constants on the intergalactic medium properties will be independent of the choice of simulation code has been used in the analysis. I wanted to highlight that this is the era where many interesting results on H1 21 centimeter power spectra are coming, although these are in the form of upper limits, but still we can use those upper limits to rule out models. We have seen that several upper limits has been able to rule out extreme models, which are mostly driven by patchy reionization and heating. And eventually, these upper limits, as it will go down, we will be able to basically flip our statistical approach, and we will try to address this issue. What is the particular properties of interactive medium at those redshifts, instead of asking this question, what is the statistical properties of the excluded model? So with this, I will stop now.
Completely on time. So we have some time for questions. Yeah.
Thank you. Raghu, I don't know, maybe I missed it, but with this new LOFA data, with your analysis, is there something new which has come up in the interpretation which was not present with the earlier upper limits with LOFAR and other telescopes?
So earlier upper limit, earlier interpretation paper with LOFAR, there our approach was limited. But here, like we have explored a much more general type of models. So their parameter, the source model which we had used, for example, that only we vary 3 parameters. Here we are varying 4 parameters. In terms of the addition of new models, what we have found, there is only at raised to 9. Previously, it was done on raised to 9 only. That time it was at raised to 9 only. So there is a little bit improvement because, the results has only gone down a little bit. Right? So there is no significant amount of improvement, so to highlight. But what we have done in the paper is that we have also added a radio background, which is now giving us more rigorous results, etc., in different type of models. But it is presenting the upper limits at different other two redshifts, which is very new. And what we are finding is broadly like the nature of exploratory models are similar. So it's now so one can actually now derive that if you have a upper limit at certain stage, what will be the set of models will be ruled out. We don't have to wait.
Thanks.
Maybe I missed that part. When you were showing that plot of power spectrum of LOFA data with the models you have generated.
This one?
Yeah.
Ah.
You have assumed that there is no X-ray heating. So how can you?
So there is X-ray heating
address
in these
it?
models.
No X-ray heating, right?
There is X-ray heating. So these are like all X-ray heating, all Lima alpha, all. These are self-consistent models. The dash lines, yes. So dash line is a particular.
Dash line.
Dash line
is,
only is the where there is no X-ray heating.
Okay. Thank you.
Sorry.
Question. Let's thank our speaker.